Okay, let's start. This is lecture 5 for CIS6395. So I will finish the networking encryption overview today. Then I will move on to the next topic, which is about virtual machine and virtualization software. So you need to set up the virtual box on your own computer. And so homework 1 is released and is due basically next Sunday midnight. So you have plenty of time. And homework 1 basically tests the questions on the networking principle and the network security part. Okay, let me continue the network encryption. So last time we mentioned this symmetric key cryptography. So this slide is important for you to understand the concept. What is a modern computer-based symmetric key cryptography? So because it's computer-based, so every data operation is on 2 to power something bits. So it's either 8 bits, 16 bits, 32 bits, or 64 bits. So that's how the operation works. And the whole operation here is basically table lookup and the bits swap. So table lookup and the bits swap, those operations is very convenient for the current computer architecture to do. So the DES is very fast can be computed by the current CPU, and it's designed use this same operation 16 round. This design basically makes sure that we can use the same digital logical circuit to do the operation and repeatedly do a 16 round. So digital circuit design will be much simplified. We just design this basic operation. And of course, every round operation, we will use a different input, 3 different input, and also different substitution table, which is called substitution box. So because of this design is using computer architecture in mind, so it's very fast for a computer to do, and also very convenient for you to design a hardware chip to realize this encryption using hardware. So that's the design principle for any kind of symmetric key cryptography right now. And we mentioned that in 1990s, people realized this key space, this 56-bit key space, was too small. So they replaced by the AES. AES is using this data key. Basically, you have freedom to choose these 3 different lengths of encryption key. So if you want more higher security, you can choose a longer encryption key. Of course, that means your computation will take more resource and time to process. And the design principle for AES is very, very similar to TES. Again, it's mutation, substitution box, and run the substitution box many rounds. So they are very similar. Actually, AES is just the algorithm chosen by the government. So it's not the only one the second generation symmetric key cryptography. There are many other second generation symmetric key cryptography, like the blowfish, twofish, serpent. There are many other. They are designed, all use the same principle as DES. Of course, their design are slightly different. The government basically choose AES as the standard for the government operation. But many security software, they may not be designed based on AES. They may be designed based on 1 or 2 or all of those encryption algorithms. And symmetric key cryptography is very fast and very suitable for computer to process. However, it has one fundamental issue. The issue is that before you do this communication, symmetric key encryption, the sender and the receiver, they need to share the common key. So that's the problem, is that how do we agree on the same key in the first place before you have a secure, reliable channel? So how can you distribute this key in a secure, reliable way? So that's the chicken egg problem for symmetric key cryptography. So that's one major challenge for symmetric key cryptography. Another is that how to hide this key from attacker when there is no secure channel. Again, this is related to that key distribution. So both are related to the key distribution. So first question, we can say that before you set up secure communication, either sender or the receiver can pick a symmetric key, then send to the other end. So both ends will agree on the same key. So the major issue is that how can you distribute this key in a secure way before you have a secure channel? So that's why people design a completely different cryptography, which is called public key cryptography. And it's very, very different from the symmetric key cryptography. Basically, it's a pair of key. And sender receiver do not share secret key. So secret key is kept if you generate a pair of this public key. You keep the secret key by yourself. You don't share it to anyone. What you share is the public key. So you can send this public key to the other end, to your friend, and you don't need to worry about that this key can be known by attacker. So basically, when you distribute the public key, you don't need to worry about that there's no secure channel beforehand. You can distribute in a public way. So that solves the chicken egg problem. So the public key cryptography, the basic paradigm is like this. The plain text sent by Alice, we say is M. It is encrypted by the Bob's public key. So basically, Bob first generate a pair of public-private key. Bob send his public key to Alice. So Alice used Bob's basically receiver's public key to encrypt the message. So this is a ciphertext. And when Bob receives it, Bob used his private key to do the decryption, and it will recover the original message. Because only Bob knows these KB minors, then only Bob can decrypt this ciphertext. Attacker only know the KB plus because KB plus is public key. It is broadcast to everyone. So attacker know KB plus, but attacker cannot decipher the ciphertext because only the KB minors can do the decipher. In this James Cruz book, it uses KB plus KB minus to represent public key, private key for node B. So that's the notation for this textbook. For other books, they may use a different notation. And the public key cryptography also have an important feature, which means the two keys, you can use one key for encryption, another key for decryption, or you can switch their position, use private key for the encryption, then use public key for the decryption. So either way, you can recover the original message. So this is a very useful property. We will explain it in a few slides. So that's the basic requirement. And so one usage for this reverse way of the encryption decryption is implemented in this digital signature aspect. Because in the physical world, we have the signature. When you sign a contract, you sign your signature on a contract, then this contract can be used in court to prove that you have signed, you have agreed to this contract. You cannot deny that you signed this physical document. But in cyber world, because cyber world, we need to do business as well. So in cyber world, we also need such kind of function. Then this contract, basically a message, is signed by using this private key. So if Bob sends out a message, Bob can use his private key to sign this, to encrypt this message sent to Alice. And this KB minus, remember this KB minus is just a signed document. We do not say this is a secret document because this document, KB minus M, this ciphertext can be easily decrypted by KB plus, which everyone knows. So it means attacker can also do the decryption. So the message itself is not secret. The function for this encryption is to, when Alice receives the message M and digital signature of the message, Alice can verify M signed by Bob by applying Bob's public key. So to recover this, once you can decipher the ciphertext, then you know that whatever contained in the ciphertext is really generated by Bob, not modified by any other people. So whoever signed the message M must have used Bob's private key, because if you can do the decryption successfully, then the message you have decrypted must be generated by using this KB minus to the encryption. And if we assume that only Bob knows KB minus, then Alice can verify that Bob has signed the message, and the message has not been modified by anyone. Because if attacker modify a single bit on this ciphertext, when you do the decryption, what you get is just unrecognizable text, basically, because encryption decryption has a feature that if you modify a single bit, the encryption decryption will totally void. You cannot recover things. So if you do the decryption, you find out you get unrecognizable like English text, then you know that message has been modified. So if you can recover the English text, then you know that it must be generated by Bob, and no one has modified the message. So that achieves the same functionality as the digital signature in this real physical signature in a real world contract things. So that's the usage for digital signature to realize the signature function equivalent to the physical world. And non-reputation just means Alice, the receiver, can take this message and signature to court to prove that Bob has signed the message. So this can also be used in the same way as the physical world contract and physical signature. And however, in the real world, digital signature is not computing this way, because in this encryption, we're encryption of the message entirely by this KB minus. However, this public key cryptography is very, very computationally expensive. I will explain the basic principle to show why it is so expensive to compute this encryption. So in the real world, if the message M is very big, then if you directly encrypt it using private key, the encryption will take a long, long time to finish. So in order to do this digital signature in an efficient way, people designed this so-called hash function, cryptography hash function. First, they use a cryptography hash function to generate a digest for a large message. So you can think that this message digest is like a fingerprint for a human. If you represent a human, the human has so many information that you may take trillions of bytes or billions of bytes to represent human. But a fingerprint can be represented in several kilobytes or several megabytes. So this is like a fingerprint to represent the human. So this message digest is the representation of the message M. This function, hash function, is called cryptography hash function. Basically, it needs to maintain this property. First, it generates a fixed size of digest. So no matter how big the original message M is, the HM, the hash value, is always a fixed bit. It's like 16 bytes or 20 bytes or 30 bytes. So anyway, it's just very, very small like dozens of bytes. So this hash function is a many-to-one mapping. So many-to-one mapping just means that it's possible that you have two messages which generate exactly the same fingerprint or message digest. So like in the human world, it's possible that you can find two humans that have exactly the same fingerprint, because fingerprint contain much less information than a whole human body. However, the cryptography hash has another feature that even though there is a collision possibility, like two messages generate the same hash value. However, given one message, it is almost impossible for you to find another message that can generate the same fingerprint. So it just means, for example, it just means in the ocean, there is always the possibility that you can find two identical fish. But given you have got one fish, it's impossible to find another fish in the ocean that's exactly the same as the fish you have, because the ocean is so big, there's no way for you to catch that particular one fish in the ocean. So this is the same requirement. Given a message X, it's computational infeasible to find a message M such that it has the same fingerprint. So that means that if you have a message M and you know the fingerprint, there's no way for you to modify the message M such that you do not modify the fingerprint. So as long as you modify anything on the message, the fingerprint will also be changed. You cannot make the fingerprint unchanged. So that's the cryptography hash requirement. Any question for this cryptography hash requirement? Okay, so in the real world, cryptography hash algorithm originally is MD5 is a de facto standard for generate this hash value, cryptography hash value. MD5 will generate the hash value is 128 bits, basically 16 bytes. So it always generates 16 bytes of this message digest for no matter what kind of message. Like for a several gigabyte video, the MD5 hash value is also 16 bytes. So that's MD5. And the MD5 is actually, the design is very similar to DS. So you can think that DS is the foundation for any kind of symmetric key cryptography. The only difference between MD5 and the DS is that DS, you need to have another input, which is encryption key. But MD5, there is no encryption key input. The only input is a message, is a plain text. But in early 2000, some researchers have some breakthrough in research. They find out that MD5 algorithm has some design weakness. So it means that now attacker can modify a message in certain way that they can modify the message without changing the message digest. So that will break the requirement for the cryptography hash. If that's the case, that means attacker can modify a message digest without you being aware that the message has been modified. So because of that reason, people quickly designed second generation of hash function. And SHA-1 is the standard used by the government. It's a 160 bits message digest, 20 bytes, basically 20 bytes. The design is similar to MD5 because everything is based on DS. Of course, it's different. So it removed that discovered vulnerability in the MD5. And so in the real world, the digital signature is computed in this way. First, for the message M, you use MD5 or SHA-1 to generate the message digest. So 16 bytes or 20 bytes. Then you use the standard private key to sign this message digest. So in this way, this KB minus HM is called signature. Basically, in here, when you do the encryption, you only encrypt on these 16 bytes or 20 bytes of the message digest. So the encryption, even though public key cryptography is very expensive, but you only encrypt 20 bytes data. So the encryption can be done very fast by computer. Then you send the message concatenate with this the signature to the receiver. In the receiver end, receiver first use the same hash function to generate the message digest for the message he received. Remember, this message is unencrypted. Then receiver use the sender's public key to decrypt this digital signature to recover the signed message digest. Then compare these two message digests. If they are equal, then receiver know that the message he or she received has not been modified by anyone. Because if attacker modified the M by a single bit, the two hash value will be different. Remember, the principle for hash is that if you modify the message, you will also modify the fingerprint. So that's in the real world how the digital signature works. It goes through this message digest first. So in this way, the encryption decryption can be done very efficiently. Only work on 20 bytes or 16 bytes of message digest. This page of slides is very important for you to understand digital signature. Any questions on this part? Yes.
So the message is okay if someone in the middle sees this one.
Yeah. So the question is that this digital signature only provides the message authentication or integrity protection. It doesn't protect the secrecy of the message. So the message itself is in plain text. So it's like in the real world, a contract may be a public document, but it only, the signature just to prove that the contract generated by the sender has not been modified by anyone. So if you, at the same time, if you want to provide secrecy, then you need to encrypt the message itself. We will introduce that a moment later. How do you provide confidentiality at the same time? So this function is provided this integrity. Remember the basic CIA requirement for security, confidentiality, integrity, and A is accessibility. So this provides integrity for the information. Okay, so it doesn't provide confidentiality, but you can always combine with other methods to provide confidentiality. So public key cryptography can solve the chicken egg problem. However, it still have its issue. Like if you dispute your public key in a public way, so you don't need to worry about attacker know this public key. However, when you dispute your public key in the cyber world, how can you make sure that a receiver get a public key is really from you, not by attacker impersonating at you to dispute this? So when Alice obtained Bob's public key from, for example, from a website, from email, from disk, how does she know that it is Bob's public key, not attackers? Because attacker can set up a fake website and say that this is Bob's public key. Attacker can send a fake email to Alice, claim that this is from Bob's and this is Bob's public key. So public key distribution, even though we don't need to worry about secrecy anymore, but still there is some issue here. So to solve this issue, solution for the internet is that in the internet, we need some trusted intermediary, like basically is like trusted middleman. It's just like in the business world, before two partners do deal business, like before they do the business in the first place, they don't know each other's reputation. They don't trust each other. what can they start the business transaction? So they start with the intermediary. Through the intermediary, they can do the business for the first time. So in the cyber world, the solution is set up a trusted certification authority. Its acronym is CA. So for the internet, it's like the certificate authority is build a public key to binds public key to particular entity. So suppose Bob want to distribute his public key to the internet, to the public in a reliable way. Originally, Bob can distribute public key by put it on his own website, but that is not reliable because attacker can set up fake website. So the Bob can distribute his public key using this certificate authority. Bob go to the certificate authority physically or use some other way, present his public key to the certificate authority. Then the certificate authority will use the CA's private key to do the encryption on Bob's public key. So this is called the digital certificate. So this is a digital certificate of Bob's public key. Basically uses CA's private key to do the encryption. So this is called certificate for Bob's public key. It is signed by the CA. So CA is like the trusted intermediary. Then when Alice wants to get Bob's public key, Alice will basically get this digital certificate, either get it from the certificate authority or get it directly from Bob. Then Alice use this KCA's public key to do this decryption to recover this KB plus. So basically first gets Bob's digital certificate, either from Bob or from other place. Then apply the CA's public key to the digital certificate to recover Bob's public key. So you may wonder, well, this one also has a chicken egg problem. How can Alice use CA's public key? How can Alice have CA's public key in the first place? Well, the first chicken egg problem can be solved by, suppose Alice is a web browser. The first chicken egg problem is solved by the web browser basically hard code some CA's public key in its program itself. So as long as you are using a real web browser program, then this first chicken egg problem can be solved because all the CA's public key, they are hard coded into the browser program. And even though there are many CA's in the internet, but their number is limited. It's not like the e-commerce website. There are millions e-commerce websites. So it's impossible for you to hard code all these e-commerce website public key in the browser. But CA, there are maybe dozens or hundreds of CA in internet. So it's still possible for you to put all these CA's public key hard coded into the browser program. So that can solve the initial chicken egg problem. So how does the internet web work, like e-commerce? Because e-commerce is built based on the secure communication and based on that the client can trust the web server they connected is a real web server. So if you connect to Amazon, then you can be sure that this website is connected is really Amazon. It's not like some fake website claim to be Amazon. So how can you do that? Because this public key infrastructure is mainly used for the web, so we will use web as example, but it can be used by some other network applications. So suppose this web server is like my.ucf.edu or an e-commerce website. The website want to provide secure communication between itself and its client, its customer. So first, it needs to distribute its public key in a reliable way. So the website just pay a fee to a CA there are many CA on the internet, so you just communicate with one certified authority. You use a side channel to present your public key to the CA. For example, you can physically send a person to the CA, or you can send US thumb drive or hard drive with the CA with this KB+, send it to the certified authority. Then certified authority will use his private key to encrypt your public key. So that is a digital certificate. Then the CA will send this digital certificate to you. So basically give to you. So this is your digital certificate. Now when a web browser, the client, like a user A is connecting to the web server, of course user A does not connect manually, it uses a browser to connect. The browser, once it set up TCP connection, which is for the web is HTTPS connection. HTTPS is a secure web connection. So once the TCP connection set up, the browser will send a certificate request to the web server. The web server send back its digital certificate, basically send back this one. And when the browser get it, browser uses the KCA plus, corresponding KCA plus. Remember, it's hard-coded in the browser to decode this one to recover this KB plus. So in this way, we can, the web browser Bob can be sure that this public key has been distributed in a reliable way. It's not a secure way, it's just a reliable way. Remember this, this kind of encryption is not secret. Anyone can decrypt this one because KCA plus is a public information. So attacker can get this and decrypt this as well. So this is a reliable way to distribute this KB plus. It doesn't need to be secret. So once it gets KB plus, then this will solve the initial chicken-egg problem for symmetric key encryption. Because when you do actual data communication, we still use symmetric key encryption like DES, AES to do the encryption because they are very fast and efficient. No one uses public key for actual data encryption because that's too expensive. So once the browser gets KB plus, the browser will pick a symmetric encryption key, like randomly pick KA. It's, for example, this is a AES encryption key. You randomly pick that key. And also the browser generates a random number. This ARM represents random number, large integer number, encrypt them by using this KB plus. These two are just the keys, so or a number, so it's still very small. You can do the encryption by using public key cryptography. And browser send this to the web server. This one is a secret because only the web server can decrypt this one. Attacker cannot decrypt this because attacker does not have KB minus. So only the web server has the KB minus can decrypt it. Once it decrypts it, the browser the web server knows that this KA is a symmetric encryption key picked by the browser. So now I know that you want to communicate with me using this secret key. The browser, the web server B will encrypt this random number using this KAB sent to Alice. So this random number is like a challenge and response. So I send you a challenge. If you respond correctly, then I know that you have got my challenge in the real time. So the challenge response is try to defend against a so-called replay attack. Replay attack is attacker capture a packet, then attacker send this packet in its original form in a later time. Even though attacker cannot decrypt this encrypted packet, but it can replay the packet to one of the sender and receiver. So to prevent that, this challenge and response is used to make sure that this communication is real time, and whoever sent me this one must get this R, and he must also know this KAB, otherwise he cannot send the cipher text. So after this, browser know that the web server have got this KAB successfully. Then all the data communication will use this KAB to do the actual data communication. Because for encryption, decryption, the efficient way is still this symmetric key cryptography. So that's how internet web works. Of course, this is very rough procedure. It's just a concept. In the real world, this KAB is not a single key. It's actually 4 key or even more than 4 key. Like for one direction, you use one symmetric encryption key. For another direction, you use another symmetric encryption key. So there are multiple symmetric encryption key used for browser and web server communication. But the concept is just the symmetric encryption key is generated by the browser and shared to the web server through this public key encryption channel. Okay, any questions for this? This page is also very, very important for you to understand. So I have emphasized one of previous slides. This is digital signature. That page is very important. And the second important, this is the number 1 important. Digital signature is number 2 important for the entire slide. Any questions for this part? Let me see, what's the question online? Can you explain about KAB? Okay, KAB is basically, it's a symmetric key, symmetric encryption key. This AB just means this is a common shared key between node A and node B. So that's the notation by the James Bruce book. So you can just think that this KAB is a symmetric encryption key, which is generated and picked by the browser node A. Node A, remember, is a browser. So the browser pick a symmetric encryption key and send it to the web server. Any other questions? Yes.
Explain again the difference between the K minus CA, K plus B, and digital signature.
So this one, K minus CA encrypt of this B plus. This entire thing is called a digital certificate. So that's called digital certificate. So as I said, this KCA minus KB plus, this is called digital certificate, or simply say certificate. If you say a website certificate, that is represented by this. Basically, a website certificate is a website public key signed by one certificate authority. So that is called certificate. Digital signature, on the other hand, is this one, KB minus HM. Basically, is the sender's private key encryption on the message digest. So that's the digital signature. So those two concepts are very important for you to understand which one is which. Yeah. Okay, so the internet web, this e-commerce, security of the e-commerce is built based on this public key infrastructure, which rely on these several principles, these 3 principles. First, the CAs are trustable. So all the trusted intermediary need to be trusted. If one of the CA has been compromised by an attacker, for example, attacker can use one of the CA to generate a certificate for those fake website, then your security will be compromised. So CAs are trustable. Secondly, client web browser have built-in CAs, basically building this CAs public key. Of course, right now the browser does not need to, suppose there are hundreds of certificate authority. The browser does not need to get to hard code all these hundreds of certificate authorities public key in the browser code. Browser basically, the certificate authority is also use something like a root tree like structure. The browser only need to get hard code the root certificate authorities information. Then it can do this information grabbing through this tree structure to get the other CA's information. So conceptually speaking, basically the browser need hard code the CA's public key in the program itself. So that will solve initial chicken egg problem. CAs are trustable. Third is the web server need have certificate, have valid certificate. If a web server does not have a certificate, but the web server provide a HTTPS connection to the client, then your browser will give a warning, basically say that even though this communication is HTTPS, the communication may not be secure because the certificate provided by the browser is not valid, cannot be verified. So that you may know those kind of things. So sometimes when you connect to a website, you may see such kind of warning by a browser, basically saying that your connection cannot be verified because this error, the certificate authority is invalid. The reason is because the web server you connected is using HTTPS connection, but the web server does not have a valid certificate. HTTPS connection means that your browser will request certificate from the web server. The web server basically gives you a so-called self-certified certificate. The certificate is not encrypted by any CA's private key. So the browser cannot verify the validation of the certificate. So the browser will give you this warning. In many cases, this is okay because maybe the website you connected haven't paid the fee to get certificate, because if you get a digital certificate, you need to pay the fee to that particular certificate authority to buy this buy this certificate. So some websites, they don't want to pay this fee, and they still want to provide secure encrypted communication. Then they will use this way. Their certificate they don't have valid certificate. They send this public key directly to the client. So the communication is still going through encrypted channel. The communication is still using this KAB, this encryption. So the only problem for that invalid certificate is that once the browser gets a public key, browser cannot verify whether this public key is valid or not. You have to assume that this is a valid public key. So you have to assume that the browser, the web server you connected is a web server, is a real web server, is not a fake web server, because you cannot verify its identity. So that's this. Some browser will give this kind of a warning, like invalid server certificate stuff. And for example, if you connect to our CIS website, if you connect to this web server, the browser will give you this warning, basically say not secure. It just means this connection is HTTP connection, which is the unencrypted web connection. So unencrypted web connection means your traffic, if attacker can capture, they can totally recover every action you have done on the browser. But if you connect to a web server, and if it shows a lock, then that means this is HTTPS connection, and the server's certificate has been verified. Because if you click this lock, you can see this certificate is valid. If you click the certificate, you can see that this certificate is issued to this website, issued by this CA. So this is there are many CA in United States and also in other countries. So this is a CA which provides this certificate to my UCF website. And if you want to see, and it also shows the validation time for this certificate. So after this time, UCF need to pay additional fee to update its certificate. And this certificate, you can see the details. It showed that this signature algorithm, basically the cryptography hash is using this SHA-256 RSA. This is a hash algorithm, SHA-256. Basically, is that, remember we said MD5 and SHA-1. So this is SHA-1 algorithm using 256 bits of the hash value. The hash value is 256 bits. And the validation time and the public key. So these show the public key of the web server. Remember, as I said, the certificate is this one. The certificate is a public key encrypted by the certificate authority. So the main thing for the digital certificate is the server's public key. So here you can see what is the server's public key is 4096 bits, the key length, and there's a public key cryptography is using RSA algorithm. I will not introduce the detail. There are several different public key cryptography. So you can see that this digital certificate actually contains a lot of information, like this CA's name, this validation time issued to which organization, and all these information. So actual digital certificate is not just an encryption of the public key itself. It actually is the public key plus a lot of text. And so that the whole thing is called digital certificate. So I provide, so in order to explain it better, I provide this PDF file. It's a clarification of encryption notation. So I will show this one. So just remember this hash function, we use HM, represent hash function, and A minus represent node A's private key, K plus represent public key. If there is no plus or minus superscript, then K represent a symmetric encryption key. So if we only say sub A, then that means it's a symmetric encryption key. And the CA refers to certificate authority. So message digest is HM. Digital signature is this K A minus HM. And digital certificate, or with so-called a certificate of a node B, is the node B's public key encrypted by the CA's private key. And in the real world, this certificate, this is just a conceptual representation. In the real world, a digital certificate contains not only the B's public key, but also a lot of content, text content. So the actual encryption is like this. This first, the certificate content is many text information plus this node B, the web server's public key. And then the encryption by the CA minus is not on the whole thing. Remember, this whole thing could be very long. So public key encryption, we always try to encrypt just the hash value, not the entire content. So the actual encryption by the CA minus is on the hash value of the entire certificate content. So that is, so this, the whole thing here is the digital certificate of a web server or any servers. It's the certificate content in text because we don't need to keep it secret. Anyone can know. And plus the digital signature on the certificate content. The digital signature basically generated by the certificate authority. Certificate authority sign this. So that is the actual digital certificate for a website. Note that encryption is on hash value. So that's why in this certificate content, you also need to specify what's the hash algorithm you used for this digital certificate. So here it shows the hash. So the like this one, this certificate. You can see it showed this hash value, hash algorithm is SHA-256. So it shows what hash algorithm you have used. Everything here will be the certificate content. And you can see that the web course is using this certificate authority, this certificate authority. Well, my UCF is using another certificate authority. This is in common RSA. So even for UCF, our different websites is using different certificate authorities certificate. So we are paying annual fee to different certificate authority to get this digital certificate. So some websites, they don't want to pay this annual fee, but they still want to provide secure communication between them, between the server and their customer. Then they can do this self-certificate. Basically, all the clients, when they connect, they will have a warning message to show up. Okay, any questions so far for this? Remember, this page is very important. Yes.
So the digital certificate, what you say, the forward key is this one.
So digital certificate basically is the public, basically the information is the public key of the web server. Digital certificate is a way for you to be able to distribute your public key in a reliable way. If you don't have a digital certificate, you can still distribute your public key to your client, to your customer. But this distribution is not reliable.
So might be qualified, right?
Yeah, attacker, if you don't have this digital certificate, then your client, when the client connects to you, the client may connect to attacker's website, but the client don't know that because they cannot verify the public key. Yes.
Are there any certificate authorities that are free?
Is there any free certificate authority? I don't think there are, but there are some certificate authorities that are very cheap. Of course, they can certify minimal information, basically. you can only put, for example, the organization. You can only show the website URL, website domain name as our organization. You cannot change the organization name and add a lot of description of the organization. So they're different level. There are many certificate authorities, but all of them need fees. How do we know if a CA is valid? So the fundamental assumption for this security is that all the CAs are trusted. So if one CA, so in the real world, CAs, they also organize in a hierarchical way. It's not like these hundreds of CAs, they are independent with each other. So for a website, all the CAs, they also organize in a hierarchical way. Basically, you can have a root CA or several root CA. So one web browser only need to have the hard-coded, the root CA's public key. Then if this certificate the web browser gets from the server is signed by a leaf CA, then the web browser can go to the root CA to get what's the public key for that particular leaf CA, then use that public key to verify a certificate. So as long as the root CA, they are trusted, then you can trust all the leaf CA. So that will solve this hundreds of CA. What if one of the CA become invalid or compromised? If they are invalid or compromised, the root CA will know. So basically, you make your trust on less entity. You only trust the several root certificate authorities, and those root certificate authorities will take care of all these hundreds of leaf certificate authorities, their validation. Yeah. Okay. And what if a server has no certificate? I have mentioned that if a web server does not have a certificate, the browser will give the client warning that your connection may not be secure. But this happens a lot for SSH server, like a Linux server, because like our department, our CS department have multiple Linux server. So we don't want to pay the annual fee for the certificate for all these Linux servers. But if a remote user want to connect to those Linux server, they are using SSH connection, which is the secure shell connection. Secure shell connection, just like the web browser, they also go through similar way, try to verify the certificate. But if the SSH server does not have a certificate, then the first-time secure shell connection will give you a warning that this is a public key given by the remote server you connect to. Do you trust this server? Because the SSH client cannot verify this public key because it's not encrypted by any CA. So if you trust, then this public key will be saved on the client, on SSH client. Then from now on, it will always use that public key to connect to that particular SSH server. So it just means the first time connection, you have to assume that you're connecting to the real one. Then after that, all the connection will be trusted and secure. So the first connection makes the client save that remote server's public key. So that is the one vulnerable part for the SSH server connection. Okay, and we mentioned before that digital signature only provide integrity. It doesn't provide confidentiality. How can we provide both? So the following few slides explain that. Suppose we have two business partners, Alice and Bob. They are two business in the internet. They want to communicate. Suppose they don't want to do the interactive communication. They want to do this communication just in one round. Assume that Alice and Bob, they have already know each other's public key. For example, both of them have digital certificate of their server, so they can distribute their digital certificate to each other. So in this way, they know each other's public key. And if Alice wants to send a confidential message, for example, confidential email to Bob, Alice basically do this. Alice will pick a symmetric session key. The KS is a symmetric session key. You can randomly pick that AES encryption key. You encrypt the message. Then you put the message encrypted by the receiver Bob's public key. Basically KB plus encryption on this symmetric session key. Then you put these two together, send to the other end. So this KS is used to the message to be confidential. This KB plus encryption is trying to make sure you can distribute this symmetric key to the receiver in a reliable way, in a secure way, because this KB plus encryption on the KS, this one is a ciphertext. Attacker cannot decrypt it. So only KB minus, only the one whoever has KB minus can do the decryption and recover this KS. So only Bob can recover this key KS. So when Bob received it, when Bob received these two concatenated message, Bob will first use KB minus in decryption algorithm to decrypt this ciphertext to recover this KS, this symmetric encryption key. Then use this recovered symmetric encryption key to decrypt this ciphertext to recover the message M. So in this way, you can have a secure communication. So this KB plus is KB minus is used for this key distribution. Any questions here? So I want you to know that there are two keys used. Each key is in charge of what functionality. Yeah.
What is the difference between this KS and the KAB that was
on this? Yeah, what's the difference between KS and KAB beforehand? Well, it's the same thing. It's the KS just means this is a symmetric key. The S represents session. It's a symmetric session key. So this key is only used for this communication session. If you set up later on, you set up another communication, Alice can pick another symmetric session key. So it's called session key. So this subscript S represents session. It's just a symmetric encryption key. And if Alice wants to provide send authentication and message integrity, basically is a digital signature purpose. Suppose Alice wants to make sure you sign a signed contract to Bob. You are not worried about the secrecy of the contract. Is a public information. So the message M will be sent in plain text, but you also put together with the digital signature of the message M. So the message M goes through the hash function like MD5 or SHA or algorithm. Then you use the sender's private key KA minus to encrypt the hash value. So this is the digital signature. This is the digital signature of the message M. Signed by node A. This A minus the encryption key, whoever has encryption key basically is a signer of this message. You put together send to other end. The receiver calculate using the same hash algorithm, generate hash value. Then receiver use this sender's public key to decrypt this digital signature, then compare these two hash value, these two message digest. if they are equal, then receiver Bob knows that the M is really sent by Alice, and no one has modified the message M. So that proves the sender authentication. So you know that this is really sent by Alice, not by some attacker impersonate as Alice. And also the message integrity, the message you receive has not been modified by anyone. So that's this digital signature. Of course, in this communication, the message is transmitted in plain text. So message is not confidential. So what if we want to provide both functions, both the integrity and also confidentiality? Then we just simply combine these two operations together. So first, you generate digital signature to put together with the message to prove this sender authentication and message integrity. Then you encrypt everything using this symmetric session key that you have picked. Then you distribute symmetric session key to the receiver by using receiver's public key to encrypt on this session key, so that only the receiver can get the session key. Attacker will not be able to know the session key. So in this way, the sender actually used the 3 keys. So her private key is for digital signature, basically is a sender authentication and message integrity. And Bob's public key, the receiver public key is used for distribute the symmetric session key. And of course, this newly created symmetric session key for actual information encryption. So you can see there are 3 keys used in this process, and each key has its own functionality. And when Bob receives it, Bob basically goes through this process in the reverse way. Like Bob first used his private key to recover the symmetric session key. Basically, go through this way to recover the symmetric session key. Then do the decryption using the symmetric session key to recover the message M and digital signature. Then verify the digital signature using this way to verify that the message and digital signature, they match. So that's the receiver end. Okay, any question for this part? So just remember, there are 2 very important concepts in modern cryptography: digital signature and digital certificate. So don't confuse these 2 concepts, these 2 terminology, and understand what's the basic representation of digital signature, what's the basic representation of the digital certificate. Of course, you need to know what's the hash function, like MD5 or SHA-1 algorithm, why they are used. And remember that public key cryptography, it's never used in actual data encryption or decryption. It's only used for key distribution, this signature, digital signature, this hash value distribution. So those kind of things. They never use public key cryptography to encrypt a large content. You only use it to encrypt like 10 bytes, 20 bytes stuff. Okay, so that's this, and just remember this assignment. You can download the Word document or the PDF document and do this assignment. And assignment you can resubmit again and again. So you don't need to wait for the last day to submit the assignment. You can, once you finish, you can submit. If you find some error, you can resubmit later, as long as it is before the deadline. So you can always repeatedly resubmit. Okay, so yeah, I only have 5 minutes, so I will go through this a few slides, and you can also do this beforehand, like So because later on we need to use virtual machine, and you need to use your own computer to run virtual machine. In all my slides, I always have the first page like acknowledgement, because I have reused some slides from different places. If you create later on, if you create your own presentation slides for any conference, for any job interview or whatever, if you reuse any content, you should always add acknowledgement or a footnote to say that, well, this picture is coming from which place. Otherwise, you may have plagiarism problem. And virtualization software, the most popular one is VMware. So VMware has a lot of virtualization software for different scenario, for different scale of network. However, we use VirtualBox in this class. As I said, this is the free software. It's totally free, and it's enough for our own experiment, because we only run on our own computer, support a few virtual machines. So that's enough for our purpose. If you want to set up a large virtualization environment, then you probably need to use a VMware software. And Microsoft have virtual PC, and which is not widely used. And the Zing, this is open source project, because all these, even though VirtualBox is a free software, but you don't have the open source. It's not open source, so you don't know the source code. The Oracle keep the source code by themselves. The open source project, that means this is totally free, and also you can see the original code for Zing. So that's why for researcher, whoever do research on virtualization, if they want to modify the virtualization some function, they always use Zing as the prototype to start to validate their new design, because you can modify the source code. So Zing is used a lot in the research community. And so there are a few terminology. First is the host OS. The OS is operating system. So this is operating system you are running on your own laptop or desktop before you install the virtualization software, before you install VirtualBox. So this is a host operating system. One computer only has one host operating system running at any time. Of course, you can install two host OS on your desktop or laptop, but whenever you start your computer, you can only choose one of them. So that's the host OS. Test OS is basically just to refer to the virtual machine you're running in this VMware or VirtualBox software. So you can run multiple test OS, multiple VM under VirtualBox, and you can set this multiple VM either separate with each other, or you can put them in the same virtual LAN, local area network, so they can communicate with each other. And the test OS will think that it is running on actual hardware. So each test OS, you can feel that it looks like it's running on its own computer. Virtual machine image, it just means each test OS, when it exists on the host OS, it actually exists as a set of files on the host OS. So this is called image files. Yes.
Two questions. First, will we need to use the virtual machine in class, or is it for homework and stuff outside of class?
The virtual machine will be used. I will use the virtual machine in class to demonstrate some concept. You can also use it in class to follow my operation to make, because many concepts I introduced in the class is a hands-on experiment using some software inside the virtual machine. So if you come to the classroom with the virtualization software installed, it's easier for you to try it by yourself. Of course, for later homework, you need to use virtualization software. Yeah.
What guest OSs are going to need for this class?
Guest OS for the we will use. Let me see. First is Kali Linux. second is Microsoft Windows, like Microsoft provide Win 7, Win 8, Win 10, those Windows OS, and we also use another guest OS is the Metasploitable Linux. So I will explain in next class, but you can check these slides and install them by yourself, because it's not hard to install them by yourself on your own computer. So I will explain them in next class. Okay, that's the end for today's class. So see you on next Monday.